evolution of CAD tools and VLSI. So we'll discuss about what are this CAD, what is the evolution of this CAD, what are the different CAD tools are available for IC flow, IC design flow, and emergence and futures of HTL. What is the difference between VHTL and Verila HTL, and what are the various design methodologies we'll be using in designing. So that we'll discuss, and the definition of Verilog HTL, and what are the various levels of abstraction that I can able to do in Verilog HTL. So that we'll see. So as we discussed earlier in the first lecture, the evolution of integrated circuit was happened in 1960. Starting from small scale integration all the way down to VLSI. Now we have moved to gigascale integration. So designing a single chip with more than billions of transistors, we call it as a VLSI, and of course we know that it is a very complicated design procedure, right? The design flow that we have seen. In the traditional way, where it includes manual translation of your design description into your logical equation and then to the schematic. In the previous slide, we have seen how from TTL to to the logic implementation, right? So that is how we have worked on. But that is okay when I have a less complexity. But when you have a more complexity, that means the number of logic density, the gate count is more, then implementing in that way is pretty difficult. Not only the implementation, the next major problem is verification. That's very important. So how you will verify this logic? You consider your, most of you might use the electron device circuit in your undergraduate, the BC547. So you'll be having a breadboard, right? And then you will be connecting your BC547 transistor and then some resistors, so and so, and LED. When you have, one transistor connection itself, you might have a lot of issues. And if you go with one more level of transistor, again, lose connections, all these things. Now you imagine for a simple gate, you require 4 to 5 transistors for a simple gate. Then you imagine when you're working on a system, how many number of transistors. And if you are using a discrete component and you're putting everything in your board, will you be able to verify effectively? 100% it's question mark, right? So verification through a conventional breadboard, right? So that's why the evolution of CAD has become predominant, right? So CAD, that is backend tools, become critical, where you might use the conventional graphic packages like PSpice, Workbench, OrCAD, so and so. So where you'll start work on a schematic or a gate level representation, where the problem with these tools are it cannot handle higher complexity. So I want to work on thousands and thousands of transistors, then it's not possible. It cannot handle. And portability, again, I'm using OrCAD and then I want to switch over to some other Spice tool. Again, this is not poor portability when I'm taking to one design from one tool to the other tool. And again, the readability at higher, for a complex design, it's very difficult. And all the above design method, the major issue is you could able to find out the final bug till your implementation. Okay, so in all above design method, the functional bugs cannot be identified till your design is implemented in hardware, and hence your total design time is pretty long. And at the end of the day, once you're completing all your design over the period of time, and then finally you find there is a bug, again you need to redo. So that's why the CAD tool becomes predominant, important, and each and every level of abstraction will do verification. So that's very important. That is possible through this CAD tools. Okay. So coming to the CAD, as I told, this conventional PSpice or OrCAD we cannot use for the complex chip design. So then what type of tools that we'll be using for those complex designs? Especially for an ASIC design, we'll use Cadence, Synopsys. So in our lab, we have Cadence 60, and now we have increased to 100 user license. And undergraduates, they are using Cadence for VLSI system design course. And Synopsys, we have both front and back end tool. We have 50 user license. Mentor graphics, we have complete front end and back end tools, and then we have 120 user license. And of course, in industry, they have their own proprietary tools. Okay, apart from the standard vendor tool, they'll have their own proprietary tools also. Okay, so apart from that, there are some tools called Magic and so on. So a lot of tools are available. Okay, so you'll be using this cadence for analog, and for analytic, we'll be using Synopsys. Of course, for DFT, those applications you can use mental graphics also. So we'll have the complete set of tools in our lab. Coming to the FPGA design, Xilinx for all Xilinx device, Intel EDA for all Altera and Intel devices, and National Instruments which will support Actel Lattice FPGAs. There is other set of simulation tool which will be used for process and device level simulation. So where we talk about fabrication, right? So that's what we call it as a process. Okay. So starting from the substrate and how you are developing a device structure. Then at the device level, again you can perform the electrical characteristics of the device. So in physics of VLSI, you'll be studying a little bit on this, right? So then that comes under device level simulation. In our lab, we have two set of tools. One from Synopsys. We have Synopsys TCAD. TCAD stands for Technology Computer Aided Design Tools. Okay. And we have Centaurus Process Simulator and Centaurus Device Simulator. It can support both two-dimensional and three-dimensional structures. Okay. Now, whatever the transistor that is available in chip is now more on 3D. Okay. And Silvaco, we have Athena and Atlas Device Simulator. And of course, we have one more set of tools. We call that as an ATK, Atomistic Toolkit. Okay. So you can work on material characteristics and interface characteristics at the atomistic level. Okay. So we have quantum wise atomistic toolkit. So these are all the flex tools that we have. So starting from the process till system level, we have all set of EDA tools. So EDA stands for Electronic Design Automation. As the name automation, that means less human intervention. Okay. So in this course, we are going to do a HDL. So what is this hardware description language? In electronics, a hardware description language or HDL is in any language from the class of computer language for a formal description of electronic circuits. Okay, and especially it is digital electronic circuits. Okay, it is a digital electronic circuits. So we'll be discussing that in detail. Okay, it is a formal language that used to describe the functionality of digital electronic circuits. So it can describe the circuit operation, that means the functionality, the design, and also to verify its operation by means of simulation. So one language which can be used for the design and for the verification. Okay, so for both logic verification and the design, we'll use same HDL. So there are two popular HDLs. One is Verilog, the other one is VHDL for any complexity. I hope some of you might already done VHDL or some might done Verilog. In this course, we'll be focusing more on Verilog HDL. Okay. Why this HDL has become important, in especially in IC design? High level language, your like Photon, Pascal, C, C++. So these are sequential in nature, whereas your HDL is concurrent in nature. Okay, and the designer needs to have a standard language to describe all digital system. One is working on schematic based, the other is working on some other design entry procedure. I want a unified standard language which will able to describe your digital system in terms of hardware. Then HDL is a common language that has been introduced to uh, define those kind of designs. Okay, and a HDL comes into existence, and these have special concept to model the concurrency process found in digital system. Okay, so what does that mean? So one is sequential, which I told your high level languages are sequential. So that means the set of instruction will execute one after the other. So after executing one first instruction, we'll go for the second, then third and fourth. Whereas in HDL, if you have 1, 2, 3, and 4, all will execute concurrently. Okay, and that's why if you see this example, okay, now I'm having A, B, and then C and D. So this gate and this gate can do can process it parallelly. So when I'm providing A and B, this gate start works, right? In a sense, it will take the input and then it will evaluate its output. Similarly, when I'm giving C and D, this will do. So there is a concurrency procedure which I can effectively model in HDL, hardware description language. And moreover, the timing related parameters that I can be able to model in HDL effectively. So what is that? I'm giving input, I'm going to get the output, but when I'm going to get this output. So model your timing delays. So that is possible with HDL. Okay, clear? So, and these have special constructs to model the concurrency of the process found in your digital system. So that's why we are using this HDLs. Future one is easy development, verification, and debugging through your HDL. And these descriptions are easily portable. So I'm right now using Cadence. I want to use this HDL in Synopsys. Yes, I want to use this HDL in Intel Quarterstaff. Yes. So you can easily port from one tool to the other tool, and it is compatible to all design tools. And it can describe digital at various abstraction level and also at the hierarchical modeling. So what do you mean by various abstraction level and hierarchical modeling? That we already discussed, starting from your transistor level to the gate level, then the module level, then submodule, and system level. So I can define at any abstraction level your Verilog HDL, and then you can model it. Okay. And what do you mean by hierarchical modeling? So that means in your HDL, for example, you have counter. Now this counter again can be designed using T flip-flops, right? Again, this can be done using D flip-flop and a NOT gate. That means I can define a lower level or a leaf cell using Verilog HDL, and the intermediate cells also in Verilog, and the overall top level. So in order to realize the functionality of a counter, if I have a D flip-flop and a NOT gate, I can able to make this counter, right? So by calling its functionality, that we call that as a hierarchical modeling, which supports hierarchical modeling. Okay, clear? So your HDL supports hierarchical modeling. And your HDL descriptions can be functionally simulated with a logic simulator, where we'll use models and simulator to verify its functionality. Okay. Why this HDL becomes more important, as your logic synthesis tool in late 1980s push these HDLs in forefront. That means how effectively this synthesis tool can understand the hardware description language and convert the equivalent hardware for it, right? So that gives the evolution of these HDL, and the digital circuits which are described at RTL level, using HDL, which is also can be synthesized through an automated logic synthesizer tool. Okay, what is this RTL stands for? Register transfer level. Okay, so all these your hardware will be modeled in this way. Okay, so your input to the output, this is reg2, reg1. Okay, so this is RTL, register transfer logic. So all your code or your design will be mapped to this particular RTL logic, register to register. Okay, we call it as a register transfer logic. So how to write the code in order to ensure that the hardware is mapping in this way? That's what we are going to discuss. RTL coding style in Verilog. Okay, so that we'll learn in this course. And your logic synthesis tool can extract the gate level details from the design automatically from your RTL description, right? That's what synthesizer will do. Fine. It's a question. What is the difference between a VHDL and Verilog HDL? So VHDL stands for Very High Speed Integrated Circuit Hardware Description Language, whereas Verilog HDL stands for Verification Logic Hardware Description Language. The differences: VHDL is designed to support system level design and specification, and Verilog primarily for digital hardware designers who are developing an FPGAs and ASIC. Both can do FPGAs as well as ASIC based design. It's now up to the designer either to go for VHDL or Verilog HDL. As you go through the language, you can able to find the difference between these two. So VHDL, requires a library. It has a library, packages. All these concepts are there in your VHDL. Okay, attributes, packages. Okay, where those stuff is not there in Verilog HDL. And this is the syntax is similar to C. Okay, close to C language. And for generally they'll tell for a complex design, it is easy to implement that using VHDL. It doesn't mean that we cannot do it, but there are a little bit of difficulties there in terms of language construct. But still, you can do with Verilog HDL also. Okay, and in earlier days, depending upon again the client requirement. So if it is a German-based clients, they work on Verilog, and US-based clients they'll work on VHL, something like that. But nowadays it's not, the difference no longer different. Most of the case now we are using Verilog HDL. Okay. In DoD, Department of Defense, earlier they started with VHL. Okay. So the difference becomes clear when one analyzes the language feature. So whatever I want to model the hardware, you can do both VHDL as well as in Verilog HDL.